let's get started with our first speaker, who is Brian Free. His co-authors are Spencer Baumgartner and Craig Lund, and his faculty advisor is Lisa Ely, which is me. Introduce myself. And Brian will be speaking on identifying channel morphology changes in response to the removal of the Glines Canyon Dam on Elwha River, Washington.
Thanks, Lisa. All right, so yes, I'm Brian Free, and I want to talk to you today about identifying the channel morphology changes in response to removal. Now let's take a look at the slide in the background. My study area is over in the Olympic Peninsula of Washington, and the Elwha River flows north into the Straits of Juan de Fuca, starting at the base of Mount Olympus, and then so it flows up towards Port Angeles. So let's talk a little bit about the objectives of my research and what I've been trying to convey here with the channel morphology changes. And I want to quantify the sediment deposition, the erosion, and the geomorphic change in the middle reach of the Elwha, just below the Glines Canyon Dam. And now what's important to understand about this is that the Glines Canyon Dam and Elwha Dam, the whole Elwha restoration project, is the world's largest intentional sediment release in history. And what this means is that there's initial estimates of 7 to 8 million cubic meters of sediment that is expected to flow from this river in the first year, so during the time that I've been doing this work, out the river and also depositing within everything. So there's expected a lot of channel morphology changes. Now this image over here on the right, you can see the Glines Canyon Dam here, the Elwha Dam, which has already been removed, and the two reaches. So my reach is between the two dams, whereas the lower reach, where USGS is working currently right now, is up at that point. And so let's learn a little bit more about the Glines Canyon Dam. It was built in 1928. It's the furthest upstream dam on the Elwha River, and it's a 60-meter concrete arch dam. And what this is doing is holding roughly 20 million cubic meters of sediment behind the dam. So 20 million times 10 times 10 to the 6. You get what I'm trying to say. And so what's interesting is, well, in September 2011, the dam removal started beginning, but they were pushing to remove the lower dam, the Elwha, prior to the coarse sediment release, which has happened in 2012. And so this is a picture of the dam removal as it was starting to get to the base of the lake where coarse sediment was being released. This is taken in September of 2012, when I was starting my initial field work, and then in October 2012 was when they finally hit the base of the lake and started actually allowing sand and gravel to start flowing in the system. And so let's talk a little bit about my research hypotheses. Now, sediment distribution on a reach scale is going to grade the channel with sand and pebble-sized sediment. And there's also going to be a detectable sediment pulse that's going to propagate downstream throughout the reach. And I expect to be able to see this throughout all the research that I've been doing. Now, between both of these here, it's important to understand that any other dam removal that has happened is 1/10 the size of the Glines Canyon Dam and Elwha dams. So we're talking 1/10, and where 7 to 8 million is expected to flow through here, 1/10 of 7 to 8 million, that's a huge difference, right? So, and then on top of that, everything that's been done shows that all the sediment deposits generally within the first 2 kilometers of the dam removal. So sediment deposits 2 kilometers downstream of the dam, and then generally it takes a year or more to flow through. Whereas my hypothesis here is saying that we're going to see this start to fill riffles and pools throughout my entire reach as it just continuously flows through, because we have 7 to 8 million cubic meters yet again flowing through. And then we have this increase in sediment as well as new large woody debris influence the lateral channel migration. So all the wood prior to this removal has actually been kept behind the dam, so it's been entrapped in the reservoir that's behind the dam. So we have a lot of new large woody debris as well as this new sediment that's flowing through. Now our study sites, I have 4 study sites that are located in Olympic National Park. This is wonderful because it's just before we start getting into human influences on the river, so trying to armor for a property or anything else. And they're located at 2, 4, 5, and 6 kilometers downstream. And each one of these sites has some sort of chance for erosion or geomorphic change. We're talking woody debris, cut bank erosion, channel widening, or mid-channel bar formation. And so we can see in this image here, this is middle reach, this is where my 4 sites are. Now let's zoom in and take a look and see what we expect at each one of these. At 2 kilometers below the dam, so the Lions Canyon Dam is right here, 2 kilometers below, there's actually a 2-kilometer bedrock canyon that is from the dam to this point. Now this is where we expect first deposition to happen and new large woody debris start to collect. And then at 4 kilometers downstream, this is an area where the dam starts to, not the dam, the stream widens. And so we expect the water to slow down and start to deposit more sand and gravel in this area. And then 5 kilometers, this is a big area where this oxbow is, and we expect to see a large cut bank erosion happening in this area, as well as a lot of woody debris start to collect in this area because of the gooseneck in the river. And we'll see some images that will show all of this. And then 6 kilometers, this is the park boundary, which is really nice. So I finally was able to get to the park boundary within a good distance. And this is an area where the channel starts to widen again, and we start to see maybe more deposition happening because we slow down again. So let's talk about the methods. I'm doing repeat surveys of before and after core sediment release. I've already stated this. And I've done this in summer of 2012 and 2013. So right now I'm processing data. And at the end of this talk, if we have time, I'll show you some real preliminary data that I just got the other day. And what I'm doing is I'm using our terrestrial laser scanner, or ground-based LiDAR, to get high-resolution digital elevation models of the surfaces of the bar. So we're talking centimeter accuracy of what's going on in elevation change. And then on top of that, in the channel where the laser can't penetrate, I'm using total station or RTK surveys to understand the channel morphology of how it's changing underwater at that point. And then to understand the distribution of sediment as it flows through the system, I've been doing bi-monthly pebble counts. So every other month, this is no longer a trip, it's a commute every other month. Where I am actually just taking surveys across the bar and trying to understand, have I changed from primary cobble to sediment, to sand or silt, or what is the surface of the bar starting to look like? And then photo documentation every time. I've got terabytes of photos, it's ridiculous. So, some of our results. Well, the first site, 2 kilometers downstream, we can see here in 2012, the water channel, the water is flowing through 3 different channels up here. We have some woody debris. And then 2013, we have a major amount of sediment deposition, as well as new woody debris here. Well, okay, I said this was going to happen. Well, what do you know, it does. What's interesting to note, though, is this is between 500 and 600 CFS flow in the river, and this is 300 to 400 CFS. However, I was here at a rainstorm at the same time, and it flowed at 1200, and it still didn't overtop that new bar. That's new elevation. So that means we've got major channel migration going off to the left-hand side here and not overtaking with new flows. Recently that's been changing, but that's not for this talk right now. Now, at 6 kilometers downstream, I wanted to talk a little bit about sediment distribution. So I told you that I could start to see the propagation of the sand and gravel flowing all the way down through my reach. Now, this is 10 months after, primarily because I didn't have time to update this, and I apologize for that. But we can see in 2012, I've got primarily cobble system at 17 centimeters. And then in 2013, we've filled in all those cobbles with sand and gravel. And you can see here percent distribution on the left and then size on the bottom. And so what this before line is the distribution of cobble to sand that I had prior, my size distribution. And we're at 50%, we're looking at 168 millimeters or 17 centimeters. And then now we see that everything afterwards is dropping out at less than 1 millimeter. My 50% level is still less than 1 millimeter. I'm way up there. And a note on sediment, I chose not to look at any finer sediments than less than 1 millimeter. For the amount of sediment that's flowing through the system, I felt like looking at silts wasn't going to be beneficial to the time that I was spending on everything. So now I'm more than happy to understand if I should change that idea. So let's talk about woody debris. 5 kilometers downstream, this is the area where we had the big oxbow, the gooseneck, where we expect to see new woody debris start to collect, as well as channel morphology changing as well. And what you can see here is I have a little bit of wood at the bottom of the image, and then I've got one channel here, another channel here, and actually what you can't see is behind these trees is a whole another one that's taking a major amount of water around as well. And then you look at this bottom image, 1 year later, I've got a major raft of wood, as well as the center channel is now all sediment. And like I said, we've got a little bit of change in flow regime, but not enough to make a big difference. This is still, within 100 CFS of each other. So we have major amounts of sediment starting to deposit and filling riffles and pools throughout the entire area. So, there we go. Now, I talked about this fancy LiDAR that I was using. So I have a couple different images here. We can see here in 2012 the extent of the LiDAR. That's everything that's in orange. This is one bar, just overlaid on a photo just for some understanding of where we are. And then in 2013, we can see new bar growth. And if you see the two, now you can see the bar growth and the channel change that's happened. Now that's a lot of channel change at 4 kilometers downstream. And we've doubled our bar in size, 7,000 to 14,000 square meters. That's a huge amount of sediment depositing in a major area. And this is an active system, so we are continuously seeing this bar actually grow and erode at this end, as we would expect to see in any river system. Yeah, it's going a little fast. And so let's talk about some preliminary data. So it should be understood that this data here I have no air analysis on. This is 3 minutes and 5 minutes. I see I'm reading things and this happens. So. This is, I have no air analysis on any of this data yet, so this is something I need to work on. So the sediment deposition estimates, we can see that same bar we were looking at just in this image here with a cut and fill analysis. We are seeing an increase of 55,000 cubic meters. And I was like, hey, this number doesn't make sense. I'm like, what the hell's going on here? And then I realized, wait a minute. We expected 7 to 8 million cubic meters of sediment to be flowing through here. And I started thinking, wow, that makes sense now. That's a lot of sediment, a lot of bar growth. Now, like I said, I have no air, so that's something we need to work on. To understand what's going on in this image here, this is elevation change. And so you can see the color change in this. So where I have the most elevation change is where most of the new sediment is deposited. And we've had, where the red is where we start to see a little bit of erosion. And then anything in the whites are basically like null and void, right? So to move on to one other one, just further downstream. So this is 6 kilometers downstream. So like I said, we expect to see the sediment deposit way downstream. And I was expecting to fill riffles and pools. And so what I can say here is, now we already looked at an image where we saw this here. We said, okay, the cobbles, okay, they filled in. Okay, the channels changed a little bit. But what's happened is we actually have seen a less, we've actually eroded some sediment that's happened here. Well, what I can say is that we actually have a new channel that's flowed on beyond where any data that I have, because I didn't expect to see it happen, as well as the sediment starting to just fill interstitially between all the cobbles, but we haven't had a major elevation increase yet. So the bar has changed, yes, in distribution, but has it increased in full in size? No, it has not yet. So do we expect to see more change happen here? Yes. I'm really interested to see what happens when I get out this summer to do one more set of data. So, in conclusions, basically, let's just restate the hypothesis. I expected to see sediment distribution, and it's not on there, sediment distribution to grade and fill riffles and pools basically throughout the entire reach. Now, I've shown that here. And then I've also said that I could watch it propagate from one bar to the next, and so we can see at between the 4 and the 6 kilometers, we can see that happening. And then the large woody debris is starting to cause some lateral channel migration, as well as the sandy sediment is propagating further downstream, like I said already. So, that's some pretty cool stuff. Now, some acknowledgements here. You can all read who you are. And so, any questions? Yes?
Several questions.
Sorry. All right,
So, what's the significance of this study? What does this mean in the real world?
In the real world,
Yeah.
the significance. Well, so how are channel changes going to be affected by us removing dams? Most dams are coming to the end of their lifespan. They're not really producing enough energy, so we have to start removing them. How do we deal with the sediment that's flowing from them? And so how can we watch and see what's happening? The further downstream where USGS was working, they're working in more of a dynamic system with the tribes, understanding how it's going to affect the different property values that are down there and everyone else. On top of that, this is an area, so we saw all that sand and gravel starting to fill within the different cobbles that are happening. This is actually allowing some new spawning grounds as well as the new woody debris, more new spawning grounds throughout the entire system. So we're talking fish and property issues. And so my study, personally what I'm looking at is how is the channel just reacting to this? How are the bars growing? Is this something that I can take further and move on and understand and say, okay, if I'm given another project, can I see and give a prediction of what's going to happen? And so.
Good. Do I have time for another one?
Yes,
Well,
there is
behind
time.
you,
Well,
Robert.
maybe we'll let some other people ask. And then
All
come
right.
back.
Yeah.
I'm just wondering, I thought I read somewhere that, let me back up. So all that sediment and whatnot is going to come through and fill the channel, and ultimately, do they expect it's then going to erode away into the sound?
Well, so some of it's going to erode away into the sound, some of it's going to stay up on the bars. The woody debris is going to do a lot of work here to really start to stabilize what's going to happen. So it's depending on what the woody debris is and the flows that are happening in the river. So this year we didn't get the 10-year flood that they were hoping for, so the sediment's really just kind of sitting where it's at. And if the wood stays where it's at for the next year or so, that sediment's really going to lock it in, and so then we might just start seeing other changes. Otherwise, if we get that flood real soon, we're going to watch it wash completely out of the system. It's going to be interesting.
Is somebody studying the effects on the sound?
Yes. Guy Gelfenbaum's watching the sound, and then some other people are watching the lower parts of the river as well.
Thank you.
So we have time for one more question.
Wendy?
Brian, if I remember Spencer's data correctly, the net change of woody debris from each site over his time, is that, were you
Yeah.
looking at the same time period, wasn't that correct?
Roughly the same time, yeah.
Yeah, so, and you have sites that have stabilized sediment and that don't have woody debris, so how do you?
So to do what I was looking at here, I took the woody debris out because it's sitting on the surface of the bar, and I can't get a good cut and fill analysis if I have the woody debris sitting right on top of the bar. I have not put that back in.
But how do you know what the stabilizing effect of the woody debris is in a situation where you have a bar that's growing extensively that doesn't have any woody debris?
I don't know yet.
Okay.
That's something I need to learn and figure out.
Okay, so you actually want to try to.
I would like to have an understanding of it. I don't think I can
Contributions
quantify it
Yeah,
yet.
no, it's similar.
I think it'd just be something that I need to get a better understanding
Yeah.
of. So.
Okay, let's thank Brian again. And we'll let our next speaker. So I think our audience has stabilized here, so we will move on with our second talk of the afternoon, and this will be given by Isabel Hong, and her faculty advisor is Lisa Ely again. And Isabel will be speaking about sedimentological and stratigraphic evidence for paleo-tsunami events at Pico, Chile.